everybody for coming along to the seminar today, for those in the room and to those who are joining us online as well. So I'll start today by paying respect to the elders, past, present and emerging of the Ngunnawal land where we're coming from today. So it's a great pleasure to have Sarah Perkins-Kirkpatrick giving our seminar today. We're quite lucky because Sarah is a Sydney based climate person who's recently moved to Canberra. So she's now just across the other side of Canberra at UNSW in Canberra. So Sarah did her undergraduate at Macquarie University, then worked at CSIRO for a couple of years, then did her PhD at UNSW, where she has become a world-renowned expert in heat waves. What else can we say about Sarah?
I always find this bit's a bit awkward.
Oh, sorry.
No, it's not you, but just in general, the introduction to just hearing about yourself.
Yeah, so Sarah is one of our chief investigators on the Climate Centre of Excellence for Climate Extremes, one of our new chief investigators. She's also this year's recipient of the Australian Academy of Sciences Dorothy Hill Medal. So it's a great pleasure to have her here with us today.
Great, thanks Nerily, and thanks for inviting me to give this presentation. So as Nerily mentioned, I do have quite a bit of a background in heat waves. I'm not actually going to talk much about heat waves today, just a little bit in terms of examples. What I'm going to talk about is another field of climate, or another field of science, I guess, called event attribution. So broadly speaking, this is where we try and detect a signal behind a change in certain extreme events, and I'll go into that in more detail. So this is work that I've got a few sub-projects on this sort of work at the moment, and it also feeds in with the Centre of Excellence. So we now have a research program that's called Attribution and Risk, and we're not strictly just doing attribution, but it's part of the research program has been sort of, I guess, influenced by this sort of field that in its current state. And I can't advance. Here we go. Okay, so what do we mean by attribution? There's lots of different ways we can do attribution in climate science, but it effectively means detecting a change in something and working out what causes that change. So it's a pretty simple term. There are different methods to do that. So for example, we might use one method to see how a long-term change in, say, temperature is driven by something like climate change and or natural variability. We might use other methods, which I'll go into a bit later, how we might detect the signal behind a specific event that we may be interested in, or how we might detect the signal behind the impacts that events cause. Generally speaking, when we talk about attribution, no matter what method you use, usually it refers back to finding the anthropogenic signal behind it. So how has that event or how has that trend or entity changed because of anthropogenic forcing on the climate system? It's not strictly that. So, a lot of the time we talk about that, we're usually talking about greenhouse gases. There are other anthropogenic forces such as, ozone, volcanic and sulfate influences. But we can also tease out things like how does, solar activity potentially affect that particular entity? How does natural variability affect that entity too? What's the role of enzo or IOD in that entity as well? But almost always, when we look at attribution studies in the literature, they almost always have a common focus on climate change. But the term itself doesn't strictly mean that. So what do we then mean by event attribution? So this is finding the anthropogenic or climate change signal behind a specific event. So usually it's extremes. So something, for example, like a heat wave, which is what I do a lot of. Sometimes a drought, sometimes a tropical cyclone. Pick your favorite extreme, and technically speaking, you can run some sort of experiment to try and isolate the signal behind that event. Again, there are different methods to do this, but one of them that's quite popular at the moment is something called the fractional attributable risk, which is what FAR stands for there. And this is basically comparing the likelihood of a specific event in a world with climate change to the likelihood of that same event in a world without climate change. And that has a heavy reliance on climate models, which I'll talk a bit more about later. But another way of thinking it is using an example here of people who might get cancer if they're a smoker. So you have one group here on the left, they don't smoke. Roughly speaking, they have a 25% chance of contracting lung cancer. However, if you compare that to a group that does smoke, again, this is all hypothetical, this bit's not based on science, they have a 50% chance of getting lung cancer. So there you can say that the odds have doubled, or your odds have doubled of getting lung cancer if you smoke. Again, it's not a sure fact that you will get it, but using that sort of with and without approach and comparing the frequency, you can work out the signal in that particular entity, which in this case is lung cancer, and how it's driven by smoking. So that's how we kind of apply that to climate science. It's effectively, you know, this has come from epidemiologists, but we effectively are applying the same sort of method. So again, it's looking at a world with climate change and a world without climate change and comparing the relative frequency of your favorite extreme event. So this far figure here is kind of showing that, so this has actually come out of a study that Sophie Lewis led, and showing that, you know, if you look at, I think this was for a heat wave, in the historical situation, you know, the FAR does change, you have some sort of uncertainty, it's not just one specific number, but it is actually lower when we look at, you know, the observed records or the historical record compared to some time in the future. So it also shifts with time as well. And it's, you know, it's a distribution of values as opposed to just one specific number. So how do we do this sort of analysis? Finding the anthropogenic signal behind the frequency and or magnitude of an observed event. So I was just talking there about, you know, comparing the frequency. In some situations, you can actually compare the magnitude. So for example, we had a heat wave, you know, our heat wave, God forbid, was 46 degrees Celsius. You know, in the past, that heat wave may have only been 43 degrees Celsius. So then we can say, well, it's, you know, 4 degrees hotter than what it would have been had it occurred in the past. That takes a slightly different methodology. That's not strictly using the FAR method, but that can also be done. In both cases, we heavily rely on climate models, and there are a lot of assumptions implicit in that they can actually simulate the climate system appropriately, but I won't go into that today. But in both cases, they must have a factual and counterfactual climate simulation. So again, the world with climate change and the world without. How they do that is different. Some models are fully coupled. So they're, you know, this is where the models from the IPCC come in. And some models are, you know, they're only run for atmospheric simulations. Some models you have, or some situations you have lots and lots of different climate models. So you're kind of sampling some sort of uncertainty with how they represent different physical processes in the climate system. Some might be multi-member ensembles where they only use, so where they have, it's the same model, but they just run the model again and again to kind of sample that window of variability. In some cases, not only do we use this factual and counterfactual simulation, but when we're looking at extreme events, we sometimes fit statistical distributions that describe those extreme events specifically. So some of you may have heard the generalized extreme value distribution, and we use this a lot to really try and sample appropriately what goes on at the tails of a distribution. So those really extreme events. As I showed on the last figure, when we look at the FAR results, we'd have a spread. So it's a distribution. We don't just say, oh, yep, that number is, you know, 0.7. We don't just rely on one number, and I'll go into why we shouldn't do that later on. So we use a statistical technique called bootstrapping to get that sort of distribution and to get that range of, yes, we're at least 90% confident that that FAR number is at least as big as or within this range, or et cetera. We try really to take the focus on just using, or off just using that one number. So as I mentioned, we can use multi-member or multi-modal ensembles. That's effectively ensembles like CMIP or SMILES. We can also use atmosphere-only models. There's one that I use a lot called Weather at Home, which is actually run on people's computers while they're sleeping. And what that actually does is can create thousands upon thousands of members of just one event. So it starts with initialized conditions, say you might start in January of this year, and it's run time and time again, maybe for a few months, or sometimes a few days, or even in some cases a year. So you know, sampling the variability around that specific event, given its physical conditions. Sometimes models that the Bureau of Meteorology, such as POEMA, are used, and sometimes we, you know, dig into these models using empirical analysis. But most often, it's more focusing on the models and how they get the frequency and intensity of those events. So in the last 15 or so years, which is roughly how long event attribution's been up and running for, the popularity has gone through the roof. So as some of you may imagine, or has probably seen in the media, it's really, you know, really big headline if they say this event was caused by climate change, or climate change killed all these people, or something like that. It's a real buzz headline. And a lot of the time, at least in recent years, if the heat wave is happening or if a heat wave's just finished, I can guarantee I'll get a call from someone in the media saying, can you say whether or not this event was caused by climate change? So there's a real push, and a lot of scientists who work in this field actually have the same push to, you know, get in there and kind of quantify that effect of climate change. Now, first and foremost, you can never say categorically if an event was caused by climate change. Hands down, you cannot do it. You can say that climate change has altered the likelihood or the magnitude or, you know, it's some other dynamical feature of the event, but you can't categorically say that it was a yes/no situation. On top of that, these studies take a long time to do. So one of these examples I have here, this is actually the first study that ever did event attribution. It was on the 2003 European heatwave, which at the time was a catastrophic heatwave, killed 70,000 people. It was really bad. It took them a year to do this study. So the method had been, you know, kind of suggested the year prior, but because they had to run the models, choose the event appropriately, you know, estimate uncertainty, do all these different things, it took them a year to actually write and publish the results. So it's not something we can do like that. And there's some sort of expectation that we can do it and we should be able to do it quickly, but that's not really the point of attribution. So these are also examples of different types of events that we are starting to attribute. Heat waves are one big one. We can almost always find a climate signal behind heat waves. Other extreme events, it's more tricky. There was a paper that came out last year looking at the human influence on the bushfire season we had that year. Also now we've been able to start doing attribution in near real time. So this is, in some cases, as the event is occurring, depending on what the type of event is, so long as we have the initial conditions of the event and we can run the models quite quickly, we can potentially give a, I hate to use the word forecast, but you can sometimes give that forecast approach, like this may be the effect if that particular event, such as a tropical cyclone, goes down a particular route. Again, we need to kind of, you know, that kind of goes against what I said about, you know, these sometimes take 12 months to do. We can do it, but that's very much as an experiment still, you know, that sort of near term or even, you know, forecast attribution. We want to aim to get there at some point, but it's not necessarily something we can do right now. It's still very much an academic exercise as opposed to, yes, we can do that. And here's the number behind that tropical cyclone being affected by climate change. Each year as well, there's a supplement put out by the Bulletin of the American Meteorological Society. And each year, do we keep going or should I? I can't see that on my screen. Do you want me to say, yeah, do you want me to keep going or you just? Is that, so that's not coming from here, like this building or? Okay, sorry. Sitting in a building with an alarm going on. Oh, okay. Wasn't sure if it was this alarm and bad timing, you might be back again. Yeah, so also every year a supplement's put out by BAMS where researchers interested in attribution choose an event that they were really interested in that occurred in the year prior and perform some sort of attribution event on it. So it's kind of, you know, not only that the people doing this research independently, but there's actually coordinated publications on, you know, in this sort of science as well. The one thing though that I will point out, and I can't actually remember if I've got it on a slide later on, is one of the issues, and there are some other issues, but one of the main issues with attribution is selection bias on our events. Normally we choose events that are high impact. So that heat wave that killed lots of people, that tropical cyclone that wiped out some poor Pacific island, or, you know, a bushfire that killed all this wildlife. You know, these are extreme events that are important to us, but there's also many other extreme events that occur that, you know, we don't do these attribution analyses on. So we don't necessarily have a clear picture or the whole picture of how climate change is affecting every type and every single extreme event. So it's just, that's important to remember if you ever see or hear something about an attribution analysis. So I have talked a little bit about FAR, which is the main sort of method we use when we're talking about how climate change affects the frequency of an event. There are two main schools. So the FAR kind of fits into the Oxford School of Thought. So you consider an event of a fixed magnitude. So say a heat wave that lasted for 5 days and was 46 degrees Celsius. And then you don't really consider the sort of physical background. So you're not really interested in what the land surface was doing at that time. You're not interested in the synoptic pattern that occurred or any other sort of dynamical interaction. You're just interested in the event magnitude. That's usually what FAR does. Then there's also another school of thought, which is sometimes what's now being done as an academic exercise in this sort of near-term forecast attribution, where you look at an event of fixed rarity. You do use your factual and counterfactual simulations. But you also consider the meteorological constraints. So for example, with a tropical cyclone, you have the observed field that you can force your model with. And you can say, well, if that observed field changes slightly, or, if you just want to sample internal variability around it, you can say, if that same event occurred in a world without climate change based on our observations, this is what it would have looked like. So there's subtle differences, but they're actually quite important. Currently, FAR is more popular, so the Oxford School, but Boulder is probably, a little bit stronger in terms of its influence or weight, if you will, because it's considering the dynamical situations, the real-time dynamical situations of that event. So it's describing that event, I guess, more broadly, or more physically than what the FAR school does. So here are two examples of how you might compare the two schools looking at the same event. Oops, I did not do that. So the Oxford School, again, sorry, all my examples are in heat waves. But you might see, you might report that you see a doubling in the increase in the 2018 European heatwave due to anthropogenic causes. So we now see that event twice more often than what we would have because of climate change. However, the Boulder School, because you've considered the dynamical influences of that event, it might be that there was a 30% increase in the intensity of that event because of climate change. So the framing's quite different. It's subtle, but it's quite different and quite important. As I've kind of mentioned in a previous slide, that's a very attractive communication tool. So here are some examples of headlines that have come out in recent times in the media. And this is where it's, the attraction is to get that one number that, yes, that event was caused by climate change. And here's that number. The media love it. So the top left there is a Siberian heatwave was found to be 600 times more likely because of climate change. Now that's a real wow factor number. And no doubt there was a huge climate change signal behind that event, but gosh, I wouldn't want to be reporting that it was that much, okay? Or at least, that's certain that it was that much. I've done it myself in the media, a number of years ago. There was a heat wave over New South Wales and I said it was twice more likely. I've now, realized that I could say that it was in the window of a certain range, but it's not good to get up there and say, well, this is the number, because we don't quite know if that's the number. We know it could be in a specific range, but if we used a slightly different modelling approach, maybe it wouldn't have been twice more likely, maybe it would have been 4 times more likely. So, then we can kind of say, yes, there's a signal there. We've got lots of evidence that there's a signal, but putting that hard number on it is not the right way to go about it, even though it is attractive from a communication standpoint. It also, so this is kind of goes on from what I'm saying there, that if you use slightly different methods, you might get a slightly different result. So a good example of this was media representation of the drought in California that lasted for a number of years, I think 6 years by the looks of it. And there was a number of different studies that in their own way tried to attribute that event to climate change, and they did it different ways. Sometimes they used that FAR method or that Oxford School. Sometimes they used the Boulder School. Sometimes they were interested in the longevity of the drought. Sometimes it's intensity. Sometimes it's impact. Sometimes it's, the area of interest change. So there's all these different factors that, are important in categorizing the drought, but that goes on to affect what sort of signal you might obtain. And on top of that, different media outlets hooked onto different studies and reported the findings. Yes, sometimes this wasn't always objective. Sometimes this was a subjective choice, but actually muddies the water quite a lot. So some papers saying, yes, this event was twice more likely due to climate change, and someone said the intensity was 10 times more likely. That message gets quite muddled. And I'm by no means am I blaming either the researchers or the journalists for this, but there are those subtleties in the methods and the subtleties in how you characterize the event that, can, make the message less clear. So all these differences in these studies were legitimate. How they defined their event at the time made perfect sense, but it's hard to communicate that across. And I don't actually have an answer. I'm not going to provide an answer at the end of this seminar saying this is how we should approach it and this is, the golden ticket to overcome that. But it's really something to keep in mind if anyone's performing attribution or even if you come across some sort of attribution assessment. So something that I've kind of touched on a bit already is defining the event. Okay, so I would argue that this is by far the hardest and arduous part of event attribution. It's not scientifically hard, but it does bend your brain a lot because you have so many different considerations. You need to consider the event as it occurred. So if you're not worried about the impacts, you're just worried about, say a heat wave or a hot summer or a tropical cyclone, you need to look at and focus on the event as it happened. So here I've got 2 examples. Again, I'm sorry, it's due to extreme heat, but the one on the left is interested in a hot summer. So they looked at average temperature over Australia. This time, this was the hottest summer Australia ever experienced in 2012, 2013. And they looked at average temperature over the entire 3 months, average over the entire continent, right? So they got a magnitude of that event that was plus 1.32 degrees above some sort of climatological average. That was suitable for their study because how their study was framed was how has climate change affected extreme summers over Australia. Another study that I led was more about a specific heat wave that occurred in May back in 2014. That only lasted for 19 days, so I only looked at the temperature averaged over 19 days. The anomaly was obviously higher because it's over a shorter window of time. And I was also interested in maximum temperature because that was the temperature that was anomalously high, not just the average temperature. So these two events, they actually came out with very different anthropogenic signals. The one that Sophie Lewis looked at, I think was 6 times more likely, or roughly, and I'm throwing around exact numbers, which I shouldn't be, but was around about 6 times more likely, or at least 6 times more likely. And the one that I looked at was at least 20 times more likely. So that can change, and this is another important thing to remember. The signal will change depending on how the event's defined. And also, mainly depending on how it's defined, and also, what time period you're focusing on as well. Obviously, as climate change gets worse, generally speaking, for at least something like extreme heat, that signal gets stronger as well. So there's also, there's uncertainty in how we define the event. That does change how, the signal you may pull out. There's also uncertainty in the method that we use. So I talked a bit about different modelling approaches that we can use, and this sort of analysis is heavily dependent on models. But if you use one set of models or one setup, you can, and will, I actually would almost guarantee you'll get a different number. That number will be different, or that range of numbers will be different compared to another modelling setup. So this particular study here did just that. They went through those BAMS reports that I talked about earlier, that supplement that's put out every year. So they looked at three years, and they pulled out events that were, they pulled out studies that looked at temperature or rainfall events. And each of those different studies had used a slightly different modelling framework. I don't know what each individual one did, and they're all legitimate, but they were all different. And what this particular study in 2017 did was put all the same events through the same modelling framework. And this one was an atmosphere only model. It had 400 simulations, so it really got that spread of uncertainty, variability in the climate system quite well. And what they found was the number or the range of numbers of the attributed signal they pulled out was really different compared to the studies in the BAMS reports. For the most part, when it came to extreme temperatures, so that's sort of this circle up here, that hot positive event, they got the direction of the signal correct, but the numbers were wildly different. Okay, so when it came to rainfall, it was a bit different. Sometimes they agreed. If it's a dark colour, it meant that it agreed with the statement or the overarching, the qualitative statement of the original study. If it's white, it meant that the signal was in the complete opposite direction. So for the most part, yes, the qualitative statement when they used the same method or the consistent method was the same as the original study, but it was a bit different when we looked at rainfall. So this, I'm not saying that, attribution shouldn't be done, but this is something to consider. You will get a different range of numbers. Hopefully that range is overlapping. But, this is why it's not necessarily great to pull out that specific number and say, yes, this is the, the number of climate change behind that event. So something that I kind of want to put out here is, should multiple methods be standardized? Instead of just using our favorite model ensemble, should we ensure that we are pulling from different types of model ensembles when we're doing attribution analysis? So not only is there uncertainty in the models that we use, there's also uncertainty in the observations we use too. So this author, this is the same author, he actually became a PhD student of mine as the previous study. And he actually found that depending on the observations that you use, so, AWAP is sometimes what we use in Australia, or if you use a reanalysis like ERA 5 or NCEP, or pick your favorite one, they categorize the event slightly differently. So, the event might have been slightly stronger in one data set than the other. So therefore you're looking at a different anomaly, and that has a flow-on effect to the models that you're going to look at. So in this example, he looked at a 1 in 10 year event. So a 1 in 10 year event in one data set, maybe, 40 degrees. In another data set, it may be 45 degrees. And if you're looking at how that number may change in observed and model conditions, in counterfactual and factual conditions, you're going to get a different anthropogenic signal behind it. On top of that, different regions have different spreads in those observations. So the different colours here, you may not be able to see it if you're at the back of the room, but these different colours are grouped in different continents. And you can see over places like Africa, the observations are all over the place. That's no surprise really, because we don't have a lot of records to feed into our gridded data sets there. Australia is even, quite similar, there's quite a large range. So in some cases, you could argue that depending on the event that you're looking at, we're going to have less confidence in the anthropogenic signal that we get, because we can't get a precise number out of the observations, or as precise as I should say. Something that you may have picked up in what I've said so far, but I think it's really important to reiterate this, is not all extreme events are equal in terms of what we can attribute to climate change. As I said earlier, if we're looking at extreme temperature events, especially heat events, pretty much always we're going to get an anthropogenic signal, and we're pretty confident that that signal is correct. This is because our models are quite good at predicting, on certain spatial scales, are quite good at predicting extreme heat. And also our observations are quite good in that domain as well. But there are most of the extremes that we experience aren't always covered well by climate models, especially if we're talking about global climate models. A lot of these really need fine scale models to be modeled correctly. So we tend to have less confidence in events like droughts, cyclones, extreme rainfall, etc., in their attributable signal. It doesn't mean that we can't do it, but we just need to keep that in mind as we're performing the analysis. On top of that, you need to make sure the models you're using are fit for purpose, okay? Generally speaking, you wouldn't want to use a CMIP class model or a global climate model to do the analysis on droughts or extreme rainfall. You want to be using a regional model that can capture those processes that feed into that extreme event well. So yeah, this can inhibit, how confident we are in some attribution statements. So a lot of the work I've spoken today has been done on international extremes, if you will. It is a bit of a different story here in Australia, and a couple of years ago, a workshop was run by the Centre of Excellence to say, well, can we say anything confident about the climate signal behind Australian events? Is it slightly different compared to the rest of the world? And we kind of came up, well, yeah, it kind of is. Our climate is highly variable. ENSO and IOD and SAM really feed into our climate in a big way. So, and then sometimes it's just not as easy to get that anthropogenic signal out if it's there compared to other parts of the world. So for example, there are some studies in the world that have found a climate change signal behind a drought, but it's much harder to do that here in Australia. I'm not saying it's impossible, but because our climate is so variable and drought's a big factor in that, it's not as easy to do. So we're currently preparing a paper, hopefully it gets done in sooner rather than later, but we've kind of categorised, well, yes, if we're looking at extreme events in Australia and we're trying to attribute them to climate change, this is the level of confidence we have in this, and these are the reasons why. So for example, if you look at heat and humid conditions, we tend to have medium to high confidence in the models, so how the models capture that event, in the observations, so whether or not we can detect that event in the observations, and also our scientific understanding on how that event occurs and manifests. So generally speaking, if we wrote an attribution statement about a heat wave, we'd have pretty high confidence that it was accurate, or with the range that we get was actually accurate. That's not the case for other types of extreme events, because of how the models simulate these events in Australia. Also, our observational record isn't always as good as other parts of the world, and our scientific understanding on that particular event may not be there yet. So we're talking about that already. So where does that leave us, at least here in Australia? We need to, so this is coming back from the same study as well. We feel that here we need to follow regionally designed decision tree. So when we're looking at an event, we need to ask a number of questions as to whether or not it can actually be attributed to climate change. So the example I've used here is based on a Northern American study, because I haven't got around to doing our decision tree yet, but you can kind of see the questions that they're asking there. So firstly, can we define the event, or how do we define it? How long did it last for? What magnitude was it? What was the spatial extent of this event? Step 2, can we estimate the counterfactual climate properly in this situation? Do we believe that our model can actually do that appropriately? Can we compare, in step 3, can we compare that event appropriately between the two lots of simulations? And step 4, how do we make the formal attribution statement? So here, this figure is actually it's based on a paper that I was on a couple of years ago, that we're actually arguing we need to step away from those hard numbers. We need to do something like this, which actually comes from the Bureau of Meteorology's ENSO diagram, if you've ever seen that, where we make a qualitative statement. It's not, here's that number, that's the signal. But here's our blocks of evidence. Here's all our model data and our observational data. We're pretty certain that this event was caused or has a climate change influence. You know, if we, you know, depending on the event and depending on the results that we get from our models, sometimes that arrow might be in a different category. So in that case, we'd say, yeah, that more likely than not, there's a climate change signal, but we don't have enough evidence to say, yes, there's a large climate change signal behind that event. Okay, so I've talked, the first half hour, I've talked a lot about event attribution. In the last few years, there's actually now started to be a focus on impacts attribution. So you can find the signal or a range of signals behind a specific extreme event. What about its impacts? So this is, you know, a rapidly growing field and one that's still very much in its infancy. But can we actually say, well, how many deaths were caused by that heat wave? How big, you know, how big is that flood? Well, you know, is that flood bigger because of climate change? How many houses, you know, blew down in that windstorm because of climate change? It is starting to happen now. So there's, you know, there's papers coming out last year on, you know, the costs that Hurricane Harvey caused because of climate change. And can you say, well, you know, 20% of those costs were due to climate change? I can't remember the number that they found, but that, you know, they did come out with a number. The paper on the right from 2016 actually determined how many deaths in Paris and London, Paris and London were caused by the 2003 heat wave. I don't actually fully agree with their methodology, and I'll go into that a little bit later, but they came out with specific numbers. So this is a really interesting field, and I fully, wholeheartedly believe that we need to explore this further, and there's a lot of merit in doing this. I'm actually heavily involved in a few studies in this area, but we need to respect and pay attention to the fact that there's additional uncertainty when we're looking at impacts attribution. So we need to remember that, you know, here I talked a lot about categorizing the event for attribution, but we also, you know, need to work out how the impact itself might be categorized. So what measure do they use to detect the mortality rate, for example? Not only that, but can that mortality rate be linked to the climate data that we have? So they tend to, they being epidemiologists, tend to have specific functions to get the sort of impact assessment or the health impacts assessment that they call it, but that may not always be transferable to our climate data. For, you know, depending on the timescale, they might be using sub-daily data. We only might have daily data available. They might use a, you know, shorter or longer window of time that we don't actually have. The resolution, they're looking at city scales, right? Our climate data doesn't always exist at the city scale level. So, you know, can it relate to climate data? And how does the attribution of the climate event relate to the attribution of the impact? So this is a really interesting question. Firstly, the FAR of a climate event does not directly relate to the impact FAR, and I'll get into that in a minute. I'll show you a diagram. And secondly, something that I haven't touched on, which is really important and a lot of people forget, is the FAR assessments are for a class of events, not a single event, which is what people commonly report, especially in the media. So just to explain how climate FAR does not directly relate to the FAR of the impact. So we might have a heat wave. This is purely hypothetical, by the way. This is not based on real numbers. We might have a heat wave over Europe that has a FAR of roughly 0.8 and it kills a certain number of people, okay? This is really tragic. I don't want to take away from that. But we can't simply say, okay, well, that event, you know, here's its number or spade of numbers that makes it related back to climate change. We can't simply transfer that to the event itself. We can't say that 80% more people died because of that heat wave. It doesn't work that way. Because we might get another heat wave that has a slightly different magnitude over a slightly different spatial domain that lasted for a slightly different amount of time that also had a similar imprint on the mortality rate, okay? And that event might have had a different FAR once again. And the third event that had an even higher FAR because it might have been really intense but for a shorter window also killed a similar amount of people. But in its entity, it has a stronger anthropogenic signal. So what we need to focus on is not simply transferring this number to this event, but working out what that transfer function or that sort of link is between the climate event and the health impact. Okay, so in all of these cases, that transfer function will be the same. So, you know, maybe days above some threshold incorporates this many people dying, and that's what you would fit to that data. And then you do the FAR assessment on that. So we might find that for events like this, there's only a 20% increase in the death rate, okay? Because, you know, different climate events, what I'm trying to get over here is different climate events or different extreme events may have a similar impact once we work it out from that sort of transfer function. So this is why we can't just simply take the FAR or the signal from the climate event and fit it straight to the impact itself. I've used the example of mortality and heat waves here, but it goes for any climate event and any impact it might cause. Similarly, FAR assessments are for a class of events, not a single event. So what FAR actually does, and a lot of people didn't realise this or don't realise this, is that FAR measures the change in the likelihood of an event at least as big as that event that we're interested in, and not specifically for that event. So I've talked a lot about thresholds, so a heat wave above 46 degrees Celsius or what have you. When we do a FAR analysis, it's not actually on that specific event. It's on events at least as big as that. So this return period plot here, it is actually focused on mortality rates. And here our threshold is deaths, deaths above, that are 34 per 100,000 of the population. That's the threshold, okay? When we fit the FAR analysis, and we can do it to this particular event, we're not trying to find the change in likelihood of just deaths that are 34 per 100,000. It's at least 34 deaths per 100,000. It's this window that I've kind of highlighted in this box. They have to be at least as big as that threshold. This can be useful, can be very useful, you know, in terms at least of impacts, you know, that might be where a system breaks. So if you have that death rate or higher, the hospital system might collapse because too many people are going to hospital. In that way, a FAR analysis might be necessary, but you cannot say that 70% of this particular number here was caused by climate change, because it's not for that specific event. So the question therefore remains, if we cannot directly fit this method, and the reason why I'm pointing this out is it has actually been done in this study down here. It was the first attempt of finding the human signal behind mortality rates caused by heat waves. You know, it was an honest mistake, and it's, you know, it's still a very interesting study nonetheless. But we can't actually do this if we're focusing on a specific event. So I thought I had another figure. So I might just skip through a bit, because I think I should probably. So this is, I'll go back a bit as well. But this is how we could do it instead. So using the same resources, you know, we need to have that sort of simulation of the factual and counterfactual world. But instead of, you know, saying, looking at that top right window, we actually, you know, need to frame the question quite differently and say, well, if an event that killed 34 per 100,000 has roughly a return period of 50 years now, what was that return period in the future? Oh, sorry, what was that return period of a similar event in the past? You can see in this diagram, it's roughly about 120, 130 years. So that event now occurs, you know, 70 years earlier than what it used to, or its frequency is roughly halved. Sorry, doubled. You know, the waiting time is roughly halved. Similarly, we could also say, well, this event has a return period of roughly 50 years. In the past, which is the blue line, what sort of event had a return period of a similar amount? And in this case, that was a mortality rate of about 24 per 100,000. So we see an extra 7 people die now per 100,000 when you see an event with a similar return period. So that's how you can do it. It's not necessarily saying at least as big as, or using that FAR method, but it's actually focusing on return periods and return levels. But the key point here is, again, you need that multi-modal framework, you need the counterfactual and factual worlds to actually get that result out. So I'll just go back to where I was. Okay. So just in the interest of time, I might just talk about where we can go. So I think I've spent a lot of time saying what the problems are with event attribution, and I by no means want you to walk out of this room thinking it's all rubbish. Why are they doing it? Why am I seeing all these papers? Why is she even here talking about this rubbish? I don't want to say that at all, because I really believe in this field, and it's something that I'm very passionate about, and it's something that I believe the Centre of Excellence can really contribute to as an emerging science. So a lot of the work that I talked about at the beginning of this presentation was using single model approaches. Now we are actually starting to move away from this as a field, and I did pose that question earlier that we probably should be doing this. We need to use this, so the figure here, which actually came out of the bushfire study, Australian bushfire study, has used multiple models. They've used different types of ensembles that have different physical configurations and also different resolutions as well. And they've combined that to get a weighted range of that anthropogenic signal behind that event. We need to minimise the bias on attribution results. So we need to, you know, again, move away from that one number and look at a distribution. And we also need to give clear reasoning when we break down that event to just one number. So when we average over space and time, We need to, effectively move away from always using the FAR method and using something like the Boulder method, where we can consider the physical setup of that particular event. Something that's not always done well is evaluating the climate models first. It's, probably a bit of a no-brainer, but can they simulate the general climate of that area? Can they get the underlying physical mechanisms of that event? And if we want to use it for impacts, and that's a big if, can we actually map that impact appropriately to that model? In some impact attribution assessments, I haven't actually looked at that first. We need to synthesize responses that use multi-method models to understand changes in hazards. So, for example, if we use lots of models and they all have different signals behind the impact, what does actually mean for that impact and planning purposes around that impact as well? And I think number 8 is really important. We must work on our communication of these events. Here I am talking about not using one number, but then it's much easier in a presentation to, say, well, the climate signal behind one event was X and Y. We must make sure we're communicating this well outside of climate science, and we must make sure we're working heavily with people in media who happen to love these studies, so they're communicating this appropriately too, and we're not muddying the waters when we're talking about specific events. So something that I did touch on, and I'm really pushing this, we need to look at qualitative statements and not hard numbers. So yeah, again, move away from that and say, well, with all the evidence that we have based on the different models that we've used and the ability to capture their event, do we have lots of evidence to really be certain that there's a strong anthropogenic signal behind that event, or do we not? And use those qualitative statements, kind of like what the IPCC does around it. So one of the points I said before was, when we deconstruct the event, don't just look at that particular, number, if you will, but consider the, the physical mechanisms around it. So one example, we did attempt to do this over at marine heatwave over the Tasman in 2017 and 2018. We looked at the pressure system that helped set up the event, as well as the event itself in terms of its intensity and longevity. You can do it in other ways. So the Queensland fire study from Queensland in 2018, we looked at the fire FFDI index, and we actually broke it down individually to the variables that go into that index. We didn't look at the index in its entirety. So instead of just saying, yes, the FFDI was X over a certain number of days, we actually broke down what each of the individual climate variables, so temperature, humidity, wind speed, and rainfall, what were their individual signals, and if we could detect a signal in the first place. So not only should we use multiple models, but we can actually use multiple lines of inquiry as well. So this is a study I think that's becoming, hopefully coming up towards the end of the year, where we haven't just used climate models and different types of climate model configurations, but also used paleo records as well. So, climate models can only go so far back in time. We rely heavily on paleo climate records to go even further back in time, and we can identify, well, over the last 2,000 years, was this event, the highest in that time frame, or was it somewhere in the middle as well? So that can go into our qualitative statements as well. I think we should also shift to a more holistic approach. So again, not just the same number, the same event, or the same model setup, but go into things like preconditioning, what were climate drivers doing, how does this particular event rank compared to other years. And a good example of this is the study that Neroli led last year on our fire weather. So I'm not sure if you actually set it up as an attribution study, but there was a lot in there that I think personally that it counts towards finding that climate signal behind that event. So I found this diagram quite useful in categorizing the different factors that go into an event and what their relative contribution may have been. So here you can obviously see that there is some focus on greenhouse gas concentrations, but it's not the only one. There was plenty of other climate drivers that went into that event. And I think in any sort of event that we're trying to attribute, we should be considering those other factors as well, and not just be focusing on climate change too. So moving forward, something that I will state, and I'll probably end on this slide, is when we're talking about impacts attribution, interdisciplinary collaboration is absolutely essential. So this is a field that I'm working in at the moment. I'm a climate scientist coming into some impacts people and say, hey, if you want to find the climate change signal behind your event, come talk to me. But we're speaking very, very different languages. They're talking about death rates or impacts that occur at city scales. I'm talking about events that are at continental scale. The methods that they use are quite different. And even though we might not think that we're quite different, we actually are. So this was actually a study that came out a couple of weeks ago, that it was a huge undertaking, and they tried to find the climate change signal in mortality rates over various different parts of the world. They made it as global as possible. I don't want to take away from this study. It's a fascinating study, and it's been huge effort. It's a huge contribution to the literature, but most of those authors are from the epidemiological field, and they've used climate model data, and that's fine, but I think it could have been integrated a bit better. And these sorts of studies do take a lot of time to get up and running. How they've brought the models into the assessment, I don't think was done as best as it could. Again, a very interesting study, but we just need to be careful that moving forward, we're getting both sides of the argument right, or both interests right when we're doing impacts attribution. We don't want to get it wrong on either side. So we've got challenges and responsibilities here. We need to ensure the information is communicated properly. We need to understand how sources of uncertainty influence the attribution assessment. There are lots of sources of uncertainty, but this isn't the be all and end all for attribution. We need to be transparent in how we approach our studies, and we also shouldn't push our tools beyond their limits. And with that, I'll leave my talk there.
Okay, well, we'll certainly start with questions from the room. And can you bear in mind that the microphone's up here? So I'm going to put it there. So speakers loudly or come up and whatever they want to hear.
Thanks for the talk. This is obviously quite a complicated field. To make it people understand, would it be possible to go through, say, like the 2014 heatwave exam?
Yep.
Say specifically how you set up like the factual, counterfactual models, and
yep.
what you did to create the numbers.
I actually had a slide that did just that, but I wasn't sure if anyone would be interested in it, so I took it out. But no, yeah, I'm more than happy to do that. So that particular study, the model runs had already been done. So in that study, I used one model that had about 20 different runs. And how those runs differed were just in their startup files for the first day, the atmospheric temperature had just been changed ever so slightly. And that actually resulted in lots of different variability among the members. They still had the same signal, but so it was estimating the variability in that particular model. So that had already been done for me. The heatwave occurred. It was, made headlines, which is probably why I chose it. It lasted, and looking back at the observational records that the Bureau had held, I worked out that it lasted for around about 19 days. So I went back, got the dates out of the observational data and came up with that anomaly, which was plus 2.52, I think. So that's how I defined the observed event. Then what I did with the models, I did the same thing. I found all 19-day heat waves. I think I did it for May. So not just the season, but just a month. And I looked at all events that lasted for 19 days over Australia, and they each had that anomaly. So they had to be 2.52 or greater. And then I did that analysis where I compared those two, the counterfactual and factual worlds. I think it was maybe 10,000 times with the bootstrap sampling procedure. And that's how you get that distribution that I showed. So in that event, I said it was 20 times more likely. That was the median result. But when I reported it, I used the lower threshold. So I think the 10th percentile, and that's where I said it was at least as big as that threshold. So this is actually probably a point I should have made clearer. Most of us tend to report, when we're speaking about the one number, that's the number we tend to report, is that 10th percentile. So we can say with 90% confidence, the estimated climate change signal was at least as big as that number, but that gets lost in translation. That's, the media forget that. It's easy to talk about that, with losing that detail, but that detail is so important, hence the push to move away from that. Does that help?
Yeah.
Yeah.
Thanks so much.
Cool.
The public policy impact of this sort of work is clearly sort of we should do more about climate change because it has this effect, and the bean counters can go away and say, oh, look at this terrible costs, we should definitely spend more money stopping those sorts of things, right? But at some point, the signal is going to overwhelm everything. And then, so the process studies, the bolder approach, that allow you to start looking at predicting.
Potentially speaking, I personally think that's the better way to go. It's a bit harder to do, but you're saying, I feel like that the fire, our fire season a couple of years ago is a prime example. Like there was a climate change element to that, sure, but it wasn't just that. So if we go and search all of the climate data and say, oh yeah, we're just looking at an FFDI value of whatever it was, well, you're going to, yes, that's important, but you also need to consider, well, what was Enzo doing? What was IOD doing? What was drought doing? So if you do it that way consistently, I'm not sure how that will change the signal that you get. Will it be less of that? It's happening all of the time. Climate change is swamping everything. And will it, I would argue it's more correct because you're considering the entirety of the event, not just, the physicality of it, not just, some random, some magnitude. How that goes into shaping things like public policy and public interest. Yeah, that's I don't know, that's a bit of an enigma, I'd say. Does that answer your question? I feel like I've gone on a bit of a tangent.
I guess I was wondering whether you could identify some of those patterns that lead to these extreme events.
Okay.
And then.
Oh, yeah, I see what you're saying. No, we potentially could, without doing the attribution analysis, we kind of knew it was going to be a bad season because it'd been so dry, because the ID was super positive and the SAM was doing something else. So you can already kind of do that, but working out the exact signal, perhaps not. One of the studies that I did briefly mention, that's what they kind of did for TC Harvey. I think they've done it for another TC now too. They had the conditions. Admittedly, it wasn't a season out, it was about a week out. And they said, right, this is the initial conditions that we have now. The cyclone can do X, Y, Z, we know that. But using that and sampling that entire range of what the tropical cyclone could do, where it could go, how intense it would get, what's the climate signal with climate change, comparing them with climate change without climate change. So you can, theoretically, you can kind of do that, and that's where it could go with the Boulder approach. And that's what we're starting to do now, but highlighting that that's still very much academic interest and not, not quite where we are yet. But that could certainly, that's why I think people are really interested in pursuing that. It can have ginormous impacts when we're talking about, well, who's going to be wiped out by that cyclone? Can we estimate the potential costs of that and mitigate that cost, before it occurs? Yeah.
So that sort of question. My question is related to what happens when you are somewhat successful with those ideas of mitigation. How do you kind of keep the momentum going when people turn around and go, well, it was never as bad as you said? So
yes.
Typical we're dealing with at the moment. Oh, well, people wore masks, things weren't as bad. Now look, all you people with your terrible predictions, they haven't come true. Why should we listen anymore? So can you sort of envisage making predictions, about what happens? The other kind of counterfactuals.
I don't have a hard and fast answer for that, but I think maybe somehow, and this is like, something that we could aspire to, is doing the modelling. Well, if we don't mitigate, this is how many people are going to die or how many houses are going to be destroyed. If we do mitigate, and try and somehow make sure that method is that message is always clear, the with and without scenarios. But I do agree that sometimes people get fatigued, and this happens with the Bureau of Meteorology now. They forecast, severe storm damage, and the storm happens, 50k south, and there's no damage. So it already happens. How to get around that though? I don't know if anyone has the answer. I feel like it's mostly in the messaging, but how to get that message over is good question.
Brad?
Obviously, the insurance industry is really, really interested in what you're doing.
Yeah.
Do they contact you directly?
They don't. I personally haven't been contacted by IAG or Munich Re or anything like that. But you're absolutely right. They're very interested in this sort of work. Especially, they're not so interested in the heatwave stuff, which is probably why I haven't personally been contacted. But anything to do with rainfall, floods, high winds, so tropical cyclones, other east coast lows, those sorts of events, they are definitely interested in. Some of the insurance groups do run, they have their own catastrophe modelling system. I know IAG has them, so I don't know if they do attribution in that, but they do sometimes their own types of simulations. But we are actually starting, I think, to partner with some of them in the Centre of Excellence as well. I don't know if they'll specifically want certain studies or certain events done, but we are definitely working closer with them at least to say, well, this is what we can do. Is this what you're also interested in terms of that anthropogenic impact?
So you said with the Boulder method, the physical conditions before an event feeding from the model you're using.
Correct. Yeah.
Does that discredit any impact of climate change on the physical conditions that are starting the event?
Great question. So that's, so we're talking, if you're doing it that way, it's the thermodynamic versus we're only interested in the thermodynamic component, however it manifests. It's not isolating how climate change also affects that dynamic component. So So Mike Wenner, who does a lot with this method, actually I think was partially his creation. I think there are other ways he does to also just isolate the dynamic component, but generally speaking, at least with the Boulder method and the FAR method in this case, it's mostly just used for that climate change signal. So what he does, that's the one that's usually used for the TC modelling. They run it, so they run the tracks or give the model the initial conditions in the runs that have climate change. So that's, historically forced, if you will, usually atmospheric only simulations. And then usually with the counterfactual world, they've just removed a climate change signal. So they might have, subtracted 1 degree Celsius somehow, or removed it that way. So it kind of accounts for that, but it doesn't, it doesn't assume, or did those dynamics shift just a little bit because of climate change? It doesn't, hasn't isolated that impact as well, but just the overall impact.
I'm just wondering about attribution of smaller but more frequent events.
Yeah.
So these ones are only extreme ones that are having a huge impact.
Yeah.
Is there attribution of smaller ones that might have more impact on people's daily lives if it's more frequent flooding or more frequent droughts, but they're not that big extreme ones?
That's a good question. I don't think anyone's as far as I know, they haven't focused on, I guess, the more moderate extremes. That sounds like it could still be of interest because I was saying, certain category of event occur more often, that pushes over that threshold, that kills slightly more people, more flooding, etc. I haven't seen a lot of studies in that way. It's a lot of them now on the bigger events, and some of the black swans, the extremes. I think because academically they're probably more fascinating because we don't know a lot about them, and also society they have the bigger impacts. So that's a good point. That there is merit in looking at the more moderate extremes.
I'm going to sneak in a last question before we wrap up. So I'm just interested that, reflecting back that attribution science was developed because Alan.
That's right. Yes, you mentioned that. Yeah.
Was he able to sue somebody for his house flooding?
Yeah. Literally, that's how it came about. Yeah.
Do you still see that as like a motivation within this field, or how is that developed?
So I actually had that figure, but I didn't mention that's what it was from. That was the original study that proposed attribution. He's basically the father of attribution. It flooded in the UK. He was pretty angry about it, understandably, and he wrote this paper in Nature saying, can we, work out the climate change signal, and therefore who can we blame for these sorts of events occurring? Can I then take this data to insurance or the government and say, give me some money? We've wildly moved away from that, I think, because of the ramifications that could have, because we now understand the uncertainty, that the method that you use, it needs to be more qualitative, not quantitative. The dynamic setting, that wasn't really something that Miles had initially considered. We could still get there, but I'm not sure if it's productive to go around suing people. I see it as tempting as it might be. I see it being more useful in saying, hey, your system is going to break, either imminently because it's about to happen in a forecast perspective, so you need to do something about that. Or in the future, if we see more of these events occurring, your system's going to break down, so try and do something now, with the risk it may cause some sort of message fatigue. But yeah, I don't know, maybe it will go into insurance and suing and liability, I'm not so sure.
Thank you very much. So, well, thanks Sarah again, and I'll remind everyone we've got coffee outside, and stick around and have a chat.